Hello, my name is Nasninowski. We're going through Monoidal category theory, the book. Okay, we're going section by section. This is chapter 3, structures within categories. And then we're talking about section 3.4, which is a mini course on self-referential paradoxes. So that's what we're going to do. It's going to be a long video because there's a ton of stuff to do and it's very interesting. Okay, so what's it about? So we're talking about categories and we're talking about structures within categories, and the simplest structure we saw in section 3.1 was a product, okay? And then later we saw limits and co-limits and all types of things like that, but the main point is, just with the concept of a product, we can see a lot of amazing theorems. Okay, just with this concept. Okay, so these amazing theorems come from something called self-referential paradoxes, and what we're going to do here is we're going to show that many of these self-referential paradoxes come from a single little theorem in category theory. Okay, what's amazing is that single little theorem, a consequence of those single little theorems, is a lot of other theorems that were discovered over the past 150 years, namely Gödel's incompleteness theorem, which shows that there's some there's some limitations of proof. Turing's halting problem, which shows that some limitations of what we can do with a computer. Russell's paradoxes about sets, and Tarski's paradox about truth. We're going to find lots of different of these examples that show certain deep limitations of what modern science is all about, limitations or problems or whatever, fundamental theorems of the past 150 years that we're going to show in one instance of category theory, one short theorem of category theory, and that's all going to work out. Okay. Okay, so we're going to back up and talk a little bit about the history of self-referential paradoxes, and that even goes back way back to 2,500 years ago with something called the Epimenides paradox. Okay, let me just state it. Epimenides was a prophet, philosopher, cantankerous old man who lived in Crete, in the island of Crete, and he didn't like his neighbors. So he used to say, "Oh, all you Cretans are a bunch of liars." Okay? Okay. The self-referential part of that is as follows, okay? Because not only was he talking about all his neighbors, but he was from Crete also. So he's a Cretan also, which means also that he's a liar. Okay, which means that this sentence that he said is also a lie. Now, there's a lot of ways of getting away from this paradox, okay, but the main point of the paradox is that what he showed is that language, the sentence, "all Cretans are liars," can refer not only to different things about the world, but also refer to language. In particular, it can refer to itself, and it can negate itself. Okay, and what we're going to do now is, for this video, is we're going to show that lots of different systems can talk about itself and negate itself. Okay, and with these negations, what we're doing is we're showing certain limitations. So we're going to see that logic can talk about itself, sets can talk about themselves, adjectives can talk about themselves. We're going to lots of different examples of these things, okay? And what we're going to find is a lot of them negate themselves. Okay, okay, so, good. Let's erase this. Okay. We're going to start with something called the barber paradox. Okay, the barber paradox is something supposedly invented by Bertrand Russell, and Bertrand Russell described it so that he can explain some self-referential paradoxes. It's a cute little puzzle. It's not serious, but it's cute, and you'll see why. Okay, so this is what we're going to do first. We're going to do a few puzzles, and then we're going to go show what the theorem actually says. Okay, I'm sorry. We're going to talk about a few self-referential paradoxes. Then we're going to, with that in our hands, we're going to have a lot of experience. So we're going to go and state the exact theorem, and then we're going to go back and do more examples of them. There are many, many examples, and I'll talk at the end. There are examples not done in the book also. Okay, so what's the barber paradox about? Okay, the barber paradox is about a barber who lives in a village, but the village is isolated. So let's talk regular. Usually, if you have a barber in a city, let's say two barbers work together in the same barber shop, okay, so this one cuts hairs and that one cuts hairs, and when there's no one else around, they cut each other's hair. Okay, so in other words, when business is slow, this one needs a barber, this one needs a barber, so they cut each other's hair. Okay, that's when there's two barbers. Okay, but what happens if you live, and this is Russell's paradox, he said, in the Austrian Alps. You live and you're in a mountaintop village on top of the Austrian Alps, and there's one barber there. And there's not an itinerant barber who goes from village to village, too isolated, and no two barbers live in the same village. So there's only one barber. And this village has the following strict rule that they follow. You either cut your own hair, okay, and then you don't have to go to the barber, or if you don't cut your own hair, you have to go to the barber. You can't have someone else cut your hair. So there's only two options. You cut your own hair, or you go to the barber. Okay? Okay, now that sounds like a plausible, reasonable thing. The problem is as follows, and we're going to explain this paradox in 4 different ways. So this is the English way. I'm just talking about it. The problem is as follows. Let's go through the rule again. You ready? Anybody who wants can cut their own hair. If you cut your own hair, you don't go to the barber. If you don't cut your own hair, you have to go to the barber. It works for every single villager in the city except for one. What does the barber do? Okay? So if you say, oh, the barber goes to the barber, but that means he's cutting his own hair. He's not allowed to cut his own hair. If he cuts his own hair, then he has to go to the barber. But he is the barber. Okay, so it's a little bit more complicated. So again, if the barber cuts his own hair, then he can't go to the barber. But he is going to the barber because he is cutting his own hair. So there's a little bit of a contradiction there, because he is violating this strict rule. He is both cutting his own hair and he's going to the barber. Okay, so that's the barber paradox. Okay, that's in English. I just want to do it a little bit more mathematically. Okay, we're going to do a lot of these paradoxes 4 different ways so we can see the structure of these paradoxes, and then when we can come to the main theorem, it's going to be easy to prove. Okay, so another way to think of it is as follows. There's a set called villagers. There are people who live in this village. Okay, shouldn't have called it a city. Okay, so there's a set called village, and then there's a function from Ville, cross Ville, to the set 0, 1. Okay, we have a better name for the set 0, 1. We call it 2. Okay, and this function tells who cuts whose hair. Okay, and so it basically goes as follows. If you have a certain villager and you have another villager, then this function will output a 1 if V's hair is cut by V prime. 0 else. Okay, so if this guy's hair is cut by this guy, you output a 1. Otherwise, if this guy's hair is not cut by this, then you output a 0. Okay, great. And now, what I want to do is, I want to talk about the rule. Okay, so let's state this rule. What does the rule say? It says, if V, comma, V, okay, now what does that say? V cuts his own hair. So if he doesn't cut his own hair, okay, that's if and only if, what? He goes to the barber. That's the rule. If you don't cut your own hair, you go to the barber. Okay, so let's write this nicely. So if v comma v, if v does not is equal to 0, it means if v does not cut his own hair, that means f of v comma the barber, okay, equals 1. Let's just say this clearly. If v does not cut his own hair, then v goes to the barber and gets his hair cut by the barber. Okay, if v comma v is 0, is 1, that means v does cut his own hair, then this is 0. Okay, very nice. Which means he does not go to the barber. Okay, now this rule works for every villager in the village. Okay, in particular, okay, it works for the barber too. Okay, so we have barber is equal to 0 if and only if f of v, barber comma barber equals 1. Now that's a contradiction. How could it equal 0 and equal 1? That's a contradiction. That can't happen. Okay, so that's the second way of describing it. Okay, great. I'd like to now describe it a little bit more categorical, namely with maps. So math is very good with a function, but now I want to be a little bit more categorical with maps. Okay, but I need a little backup, and I need to talk a little bit about characteristic functions and things like that. Okay, so this is a preliminary for the rest of this talk, because we're going to say this phrase, we're going to say some phrases over and over. Okay, take a function g, and the function g goes from a set to the set 2. Okay, now we saw this already in chapter 1. This is called a characteristic function. This is called a characteristic function. And what it does is it describes a subset of elements of S. Okay? It describes a subset of elements of S. Okay? Those things that land in one is in the subset. Great. Now I want to talk about another function. And this function goes from S cross S to 2. Okay, now this is, you can think of it as a characteristic function, but it's not really a characteristic function. What it does is it compares two elements in S, and it gives an output of them. So you're going to have S and S prime, and you're going to either get 0 or 1. Okay, very nice. Okay, so this has one input, this has two inputs. Okay, great. So let's say I fix one of the elements here. I fix one of the elements. In other words, in computerese, this is, I make this hardwired. I put in one of the elements here. Now, there's still an input here. So this is a function also from S to 2. Okay? Now, this function accepts two inputs, but if you fix one of the inputs, you still have left over one of the inputs, and that's a function from S to 2. And now we're going to ask the following question. Okay? Ready? Let's start over from here. You're given a function g. You're given a function f. And you're going to ask this question as follows. Is there a S0 member of S? Is there some element such that g, that's some type of function from S to 2, okay, is equal to f of lunar space, comma, S0. Okay? Question mark. Is there an S0 in the set such that this is true? In other words, whatever input here is going to output a 0 or 1, and if you input it in here, it's going to output a 0 or 1. Basically, these two functions from S to 2 are the same functions. Okay, that's a question we're going to ask over and over and over. Namely, you're going to be given a characteristic function, and you want to know, is there some S0 such that this characteristic function is equal to this function with one of the inputs hardwired? Okay, if so, we say G. If yes, then we say G is represented by F. In other words, we can represent it. Okay. We can also say representable. Okay, by F. G is represented or representable by F. Okay, and we're going to ask that question over and over. Okay, great. So this is a typical question we ask over and over, and it's all about characteristic functions. Very good. Okay. Let's go back to our barber paradox. Okay, and we have as follows, and I told you now we're going to do it more categorical. We have this function F, which takes pairs of villagers, could be the same one, and outputs that. Now I want to take the set of villagers, okay, and I want to use the diagonal map. This is where we need the product. Okay, so that's a Cartesian product of sets, and we need this notion of a diagonal thing. Okay, and let's just remember what it does. It takes a village V to V comma V's. Okay, and so what does this function do? This composition of function does. It takes a village V, goes to V comma V, and evaluates it on itself. So this is about self-evaluation. Okay, it's about V being compared to V. This is where the core of that self-reference is all about. Okay, but now I want to compose that with another function called not. Let me tell you what not is. Okay, not is the negation function, and basically not of 0, this is 0 and 1, this is 0 and 1, is equal to 1. Not of 1 is equal to 0. Okay, so I describe this function. I construct this function. It's a composition of 3 maps. Okay, and when you compose them, we're going to call this map G. Okay, let's clearly write down the definition of G. G is equal to, first do the delta, then do the F, then do the not. Okay, so let's be careful. This is G of V is equal to, that's V comma V, that's F of it, and that's not of F of V of V. Okay, now let's look at it. G goes from villages to 2. Okay, so it's a characteristic function. Any function that ends up here is a characteristic function. So I'd like to know, what does this function characterize? Okay, and the answer is those things that go to 1 here. Okay, let's go through that. What goes to 1 here? Well, those things that go, this is defined as this followed by this by this, so those things that go to this. Okay, what is that? Okay, these are, okay, so G of V is equal to 1 means what? It means that it was 0 here, and then it went to 1, and so that's basically, a G of V means if and only if F of V comma V equals 0. Let's see what that says. It says G of V is equal to 1. That's what it means to be a 1. The only way that can happen is if it went like this, and you get a 0. So what is G? What type of people, what type of villages does it characterize? It characterizes those villagers who do not shave themselves. Okay, those villagers who do not shave themselves. And now we ask the same question as we asked before. Ready? Okay. G is a legitimate function from two things. F is a nice function like that. Question: is there a S0? Let's call it V0, such that G of blank is equal to F of blank comma V0. Okay, another way of saying it is G representable by F? Okay, is it represented by F? Okay, and you would think, you know what, it probably is. Who would cut all the hair of people who do not cut their own hair? And the answer is obvious. The barber should. So we would think that the right answer for this is G of blank is equal to F of blank comma barber. Okay, let's see what that says. That means those people who do not cut their own hair, in other words, if there's a 1 here, those people go to the barber. Okay, we'd like to think that. Okay, the problem is as follows. Well, this should work for all V. Okay, that if you plug in G of V, if G of V cuts his own hair, that means, if G of V if G of V does not cut his own hair, that means he goes to the barber. Okay, so G of V is those people who do not cut their own hair. Okay, this should be true. However, this should be true for all V. In particular, it's true for the barber. Okay, is equal to F of barber, comma barber, close parentheses. Okay, there's only one problem. G was defined to be not F of F. So G of the barber, by definition, is equal to not. That means swap the 0 and 1. F of barber, comma barber. Okay, so how could you tell me G is equal to that? This is 1, this is 0, this is 1, this is 1, this is 0, 0, when this is exactly what it was not chosen. This is the way G was defined to be the negation of that. Okay, conclusion, it is false to assume that G can be represented because it was made to be not represented. That's exactly what this says. It's made to be not represented. Okay? By defining it as the not, that means it cannot be represented by anything. Okay? That's very nice. Okay? And so that's the categorical version of the barber paradox. We created a morphism that cannot be represented. Okay, so this is a third way. Again, we talked about the barber paradox. We did it mathematically with this F function, and now we do it with this G function more categorically. I just want to show you another way of talking about the barber paradox, which will arise over and over. Okay, and what it is just another way of looking at this F function. So what's this F function? Okay, well, it's a function that takes a villager and takes and outputs another villager. So we might write this as this: v1, v2, v3, v4, v5, v1, v2, v3, v4, v5, and the output of this matrix, the output of this function will fill in this matrix. Okay, so let's say V1 cuts his own hair. So we put a 1 here. Okay, by the way, if V1 cuts his own hair, I have to put this This is on page 114 of the book. Okay, so there's a nice little picture of it. I say, this is the cutter. This is the person who cuts hair, and this is the cuttee. I don't know if that's actually a word, but that's what I made up. Okay. Okay, great. So V1 goes to the barber. The V1 cuts his own hair. That means V1 does not go to this guy, he does not go to this guy, he does not go to this guy, he does not go to this guy, etc., etc. V2 doesn't go to V1. Let's say V2 goes to the barber. So let's imagine for a second that B4 is the barber. So we'll write it as B4. So this is the barber. Okay? So V2 does not cut his own hair, he goes to the barber, which means everything else is 0. Okay? V3, let's say V3 does go to cut his own hair. Okay? And therefore he does not go to the barber. Okay? Okay, let's talk about V5. V5, let's say, cuts his own hair. Okay. Okay. What about the barber? Does the barber does not go to V1, he does not go to V2, he does not go to V3. Okay? Question is, what does the barber do? Does the barber go to the barber? Okay. Ba 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 ba. Okay. Great. Now, I want to explain to you what this is. Every one of these every one of these columns is essentially a function from the villagers to 2. Every one of these columns is a function that outputs either 0 or 1. Okay? And we're asking the following question. I'm sorry, I didn't say this right. Sorry, let's restate that. You ready? Every one of these, VI, is a column. Okay? And you want to know what the output is. Okay? And the output is usually either 0 or 1. Okay, depending on if VI cuts that person's hair or not. Okay, great. Now, what we did here was we invented a function called G. And what's G? G is basically these diagonal guys. Okay, the diagonal guys. Okay, and we're asking the following question. By asking if G is represented by any VI, what we're asking is as follows. Question, is the diagonal the same as any single column? That's exactly what we're saying. Question, is this diagonal that we created, is it the same as any column? And the answer is, well, it could be this column, it could be this column, it could be this column, etc. The main point is as follows. It works out, it could be any column, except it can't be the diagonal where the diagonal meets the column. Okay, why? Because they have 2 different rules. The column says, okay, go to, well, the answer is, if this is 0, this will be 1, this will be 1, this will be 0. So that's why I put a question mark here, because it doesn't work. Okay? The main point is as follows. No column can equal the diagonal. In particular, the column of the barber cannot equal the diagonal. Okay? Okay, and that's the problem. The reason why the column and the diagonal is because at the diagonal we're going to have a meeting of the diagonal and the column, and they're defined to be the exact opposite. They're defined to be different. Okay, so this is a matrix way of looking at it. Okay. Okay, so that's nice. Okay, so that was the first paradox we're going to deal with. And like I said, Russell invented this paradox to explain certain things. Okay, so the next paradox we're going to talk about is Russell's paradox. Okay. Okay, Russell made up the barber paradox, or supposedly made it up. It's contentious what he did or didn't do. Anyways, he made up the barber paradox to talk about self-reference because he had a deeper result, a more important result, that's at the core of mathematics. Okay? And this is called Russell's paradox. And it's about sets. Okay, and the idea is as follows. Sets can be a lot of different things. It contains shirts, it can contain pants, whatever. It can contain books. You can have the set of ideas. You can talk about the set of numbers, etc., etc. But sets can also contain sets. Okay, you can have sets. For example, the set of students in the class. Well, every student is a set of their cells or something like that. Okay, so you can have sets within sets. Okay. And sets can contain sets. That's the main point. Okay. Now, he came to a paradoxical result with this, and let me show you. So, certain sets can contain sets. For example, you can have the set A, which has the object B, the object X, the object Y, and then you can have the set B, which contains the object A and the set A and the object Z and the object W. Okay, so this is a set that contains another set. Okay? Okay, but then you can have another set called C, and C can contain, I don't know, the letter M, the set A, the set B, and then it could also contain the set C. So this is a set that contains itself. Okay, and that's interesting. Fine. Okay, so if you allow sets to contain themselves, you get some interesting things. Okay, now if you don't like sets that can contain themselves, so then you could talk about R. R for Russell. This is an important set. Okay, and what's R? R is all sets S such that S is not a member of S. Okay? S does not contain itself. Okay? And so, for example, we'll talk about, let's say A does not contain itself. So A is a member of R. Okay? B does not contain itself. It contains another set, but it doesn't contain itself. So we say B is a member of R. As opposed to that, C does contain itself. Okay? And so we say C is not a member of R, because it does contain itself. So this is the Russell sets. This is only the sets that don't contain themselves, and C does contain itself, therefore it's not in R. Okay? Great. That's perfect. Now, again, I'm going to explain this paradox in 4 different ways: English, math, category theory, and also with matrices, but we'll see it over and over. It's the same 4 ways that we did before, but let's talk about it in math. Okay, great. I'm sorry, let's talk about it in English. Ready? Now I ask you a simple question. Is R an element of R? Okay. Is R a member of itself? Okay. And if you say yes, well, what does it take to be a member of itself? Well, it takes that it's not containing itself. Well, so that this implies that R is not contained in R. So if you assume that R is in R, then what does it mean? Why is C why is A in R? And the answer is because A doesn't contain itself. So if R is in R, then R doesn't contain itself. Okay. Now let's go the other way. If R doesn't contain itself, then what do you know? Well, then it satisfies the requirement to get into R, and so that R is in R. Okay, so you have this contradiction. If R is a member of itself, R is not a member of itself. If it's not a member of itself, it's a member of itself. This is just exactly like the liar paradox. I am true, I am false is if it's true, it's false. If it's false, it's true. So we get back the same thing. So that's a contradiction. Okay, good. Let's look at it from a more function theoretic point of view. Okay, and the idea is as follows. There's a set called, there's a collection of objects called set. We'll think of it as a category, but no, don't even think of it as a category. There's a collection of things called sets, and there's a function from set cross set to the set 2. Okay, and this function is going to tell whether or not a set is an element of itself, if one set is an element of the other set or not. So f of s, s is an element. Here's a set s, comma s prime. Here's two sets. Okay, it's either equal to 1 or 0. That's what 2 has. So it's 1 if S is a member of S prime, and 0 if S is not a member of S prime. Okay, great. Okay. Now, let's talk about this set R. What is this set R? It says as follows. If S does not contain itself, that's exactly what it says. If S does not contain itself, okay, here we're talking about two different elements, but here we're talking about the same element. If S does not contain itself, if and only if, then by definition, f of S comma R. So this is the definition of what R is. R, if a set doesn't contain itself, then that set is an R. That's the definition of R. It's all those sets that don't contain itself. Now this is true for every possible set S. This is true for every possible set S, including R. And so we get R comma R is equal to 0 if and only if f of R comma R is equal to 1. That is a contradiction. And we can't have that. Okay? So that's a contradiction. Okay. So that's a very nice way of looking at it mathematically. Okay? And the definition of R, that this is true for every single set, is inherently false. By the way, this is very similar to, we had the rule about shaving, and then we said it's true for every single villager, and in particular we did it for the barber, and we got the same paradox. It's the same thing over and over. Okay, great. Let's do it a little bit more categorically. You have set cross set. You're looking at pairs of sets. You're mapping it to 2. You have set with a diagonal map. You have this as F, and you have this not, which swaps the zeros for the ones and the ones for the 0. Okay? Okay, great. When you compose these 3 maps, 1, 2, 3, you get a map G. Now let's see what G is. G is a characteristic function because it goes to this 2, and it is going to be either 0 or 1. And if you look at it and say, what does it mean for G of S to equal to 1? Okay, well, in order for G of S to equal to 1, that means this whole thing is 1, which means this thing is 0. The 0 changes to a 1 here, okay? And so what does it mean? This. So it means that f of S comma S is not equal to, is equal to 0, not equal to 1. So it's equal to 0. Okay? Okay, so G is a characteristic function, and it describes all sets that do not contain themselves. Very nice. Okay, and now we want to ask the following question. Is there some set, or is there some S, or is there something that represents G? Okay, so again, we constructed G, and now we're asking, is there something that's represented? So let's see what that would mean. That means that G would equal to F of S, F of something, comma, well, what should represent it? Okay, well, how about the set of all sets that don't contain themselves? That's a good try. So let's try that. So that's the set R that contains all sets that don't contain themselves. So if you're going to say that G of S represents it, I'm sorry, G of S is equal to 1 means that S doesn't contain itself. Well, then this is 1 if and only if this is 1. Okay, if you plug in a set here, you're going to get that. So let's do that. If you plug in S, you're going to get this. So if this is equal to 1, that means S doesn't contain itself, and therefore S is a member of R, because that's the definition of what R contains. If this is 0, that means S does contain itself, then this will be 0, and which would mean S is not in R. So that's a good idea for saying that this works. Okay? The only thing is, this is supposed to work for all S, and so we get G of R, including R, and so we get G of R is equal to F of R, comma R. Okay? If you want to say that this function is represented by R, that means it's true for all S, including this. Okay? And the problem with that is the way that G was defined. G was really defined for input R as not F of R, comma R. Let's just make sure. R goes here. This comes to R, comma R. This goes to F of R, comma R. And this is not. So how could G of R both be F and not? Not is a function that changes, zeros for ones, ones for zeros. So it can't be that this thing is true. Let me say it another way, which is better. G cannot be represented by F, and a more important way of saying it is G was constructed to be not representable by F. The fact that this is a definition of G means it cannot be represented by any R. Okay, so that takes care of that. Okay, so that's a more categorical answer. Okay, and now I'd like to look at it from the set, from a matrix point of view. And it's almost the same matrix as we had before. So let's do it again. You have F, and this is set, and this is set, and you might have S1, S2, S3, S4, S1, S2, S3, S4, S5, S5, okay, and you'll have zeros and ones depending on whether this is a member. So let's go through it. This might be something like this. Goes on forever, and this goes on forever. I'm assuming my collection is countable, but not really. I'm not really making any assumption like that. Okay, let me just change this to a 1. Okay, great. Now what am I doing? I'm looking at a particular subset. Okay, I'm looking at a particular subset of elements. The subset of elements that do not contain themselves. So this S1 does not contain itself. So I'm going to make this into a 1 because that's the guy I'm interested in. I'm interested in all subsets that do not contain themselves. This S2 does contain S2, okay? And so that's not what I'm interested in. Okay, let's do S3. S3 does not contain itself. That's what I'm interested in. Okay, what this R is, R for red, is I'm describing this diagonal is all the elements here. Okay, S4 contains itself, therefore he's not in the set R. Okay, S5, that's an S5, S5 does not contain itself, therefore it's in the set R. Great. Okay, and now I'm asking the following important question, namely, this set, this diagonal set, and these arguments are called diagonal sets, this diagonal set, this is the set R. Question, is R a row of any of these things? I'm sorry, is R a column of any of these things? And the answer is no, it's not a column. Why? Because it's different from this column in this first position. It's different from this column in the second position. It's different from this column in this third position. It's different from this column, it's different from this column, it's different from every single column. Conclusion, R, these are every column, this is every column, is not equal to G. G is really the characteristic function of R. So we created this diagonal, or we found this diagonal of sets, and what it is, the way we found it is we looked at all the diagonal elements and we chose those which have a zero in it, not those who have a zero in it, okay? And so we get this infinite set, okay? But the main point is this infinite set is not the same as this column, it's not the same as this column, it's not the same as this column, it's not the same as any column, because it was created to be different than every single column, okay? Conclusion, R doesn't work. Okay, doesn't work. Okay, now, how do you solve this paradox? First of all, you have to understand that this paradox is at the core of mathematics. All of mathematics is built up about sets, and here I come along and say, you know what, there's a contradiction about sets, because I can define a set, R, which has contradictory properties. It's a member of itself, or if and only if it's not a member of itself. You can't have contradictions in mathematics. Okay, so this is a problem. Now, what set there is, this was discovered by Russell at the turn of the 1900s, in the early 1900s, and what set there is due to solve this problem is we say, you know what, R is a different form of a collection. Okay, R doesn't really exist as a set, it's now something called a class. Okay, and they make a whole big thing about this distinction between class and set. Okay, and what they're doing, the reason why they're doing it is because they don't want any contradictions in their set theory, and so that's what they do. Okay? We're just saying a simpler thing, namely, what we're saying is any collection of set, okay, cannot have this R in it. Okay? It won't be totally defined. It won't be defined. I mean, R will not be in this collection. Okay, so that's a very nice thing. Okay, great. Next. Okay, so we did the barber paradox. We did Russell's paradox. Now I want to do a third one, and this is called Grelling's paradox. Named after Mr. Grelling, I assume, or Mrs. Grelling. Okay, it's also called the Hetrological paradox. Okay, let me tell you what it's about. It's about adjectives. Okay, what's an adjective? It's a word that describes a noun. Okay, and so let me go through some examples. The word English. Okay, here's the question. Is English an English word? And the answer is yes. English is an English word. As opposed to that, is German a German word? And the answer is no, German is not a German word. Germans don't use the word German, they use the word Deutsch. Deutsch is a Deutsch word, okay? But German is not a German word, okay? And so these are, what we do is we have a classification of all different types of words. We're going to split all types of adjectives into two lists. Here we call them autological. These are words that describe themselves. And here we call them heterological. Words that do not describe themselves. Okay, so let me give you an example. A noun is a noun, so it describes itself. A verb, well, a verb is a word. A verb is not a verb, so it doesn't belong in there. Okay, let me give you another one. Unhyphenated, I write out the word unhyphenated, is unhyphenated. Hyphenated is hyphenated. I'm sorry, hyphenated is not hyphenated. Here's well, the book has a few more, but let me just do one more. Polysyllabic, that means made out of many syllables, is polysyllabic. Polysyllabic. English majors can figure out how many syllables there are. Okay, as opposed to that, monosyllabic, okay, that means made out of one syllable, is not monosyllabic. Okay, so, okay, monosyllabic is not monosyllabic. So, let me just state what the paradox is. You have some English adjectives are autological, some are heterological, okay, and you have the word heterological that describes those that do not describe themselves. And now you ask yourself the same question. Okay, question. Is the word heterological heterological? Question mark. Is the word heterological heterological? Okay, and now we have two possible answers, yes and no. Let's go through it. If heterological is heterological, what does that mean? That means that it does not describe itself. Therefore, heterological is not heterological. Okay, this says heterological is heterological, which means it describes itself. Okay, so if heterological is heterological, if it does describe itself, then what does it mean to be heterological? It does not describe itself. And if it does not describe itself, then what does it mean to be an adjective that doesn't describe itself? Then it's heterological. Okay, so you get the same contradiction back and forth. Okay, we're going to do this a little bit quicker. We're going to do the same thing, almost the same way. Okay, so let's do it. You have a set called adjectives, and you have a function f from, you have a function f from adjectives cross adjectives to the set 2, and basically f of a, an adjective, and a prime is an adjective, is equal to one of two things, 1 or 0, if a is described by a prime, else we do that. Okay? Okay, and now we do the same thing as we did before. Okay? What is the definition of a word that's heterological? So an adjective is heterological okay, in other words, an adjective A is described by the word heterological if and only if, ready, f of a comma a is equal to 0. Okay, so let's do that carefully. If A does not describe A, if A is not described by itself, then A is heterological. That's exactly what this means. Okay, and this is true for any A in the set adjectives. Okay, good. Any, including the word adjectives. So what we get is f of heterological, comma, heterological equals 0 if and only if, I'm going to plug in A to be heterological, f of hetero, comma, hetero equals 1. That's a contradiction. That's a real live contradiction. Okay? The proof is the same as before. The idea is the same before. Let's just go through it. What's a barber? A barber is someone who shaves everybody who doesn't shave themselves. What is the set R? It's the set it's the set that has all the sets that don't contain themselves. What's heterological? It's the adjectives that do not describe themselves. It's the same words. I'm just changing. It's the same phrases. It's the same makeup of the argument. I'm just changing the words. Okay? Let's do the same thing for. Let's do the same thing. Categorically. Okay, and so what do we have? We have adjectives cross adjectives to 2. We have that not map again. 2. We have adjectives. We have the diagonal map. We have G. And it gets simpler. Okay, and now we ask ourselves, G is a map that goes from adjectives to 2. Question. I'm sorry. G is a characteristic map. Okay, so what does G describe? Well, G of A is equal to 1 if and only if. How do you get to 1 over here? Well, you get to 0 here. If and only if f of A, comma, A is equal to 0. That's the definition of, so that's the definition of what G is. So G is the characteristic function of all adjectives that do not describe themselves. Great. Now we ask the following question. Can G be represented by any A? Okay. So can we describe all words, all adjectives that do not describe themselves? You know what? We have an example. H for heterological it describes all words that don't describe themselves. Okay? So this should be true for all A. Okay, let's go through this. If this is a 1, G of A is 1, that means A does not describe itself. Therefore, A is described by heterological. Heterological describes A because it doesn't describe itself. Okay, great. Now, this is supposed to be true for everything, including G of H should equal to F of H comma H. Okay? But 1 second. So, again, if if G can be represented by F with H, then you would have this. But you know what? G was defined following this as G of H is equal to not F of H comma H. Let's just make sure we have that right. H goes here, this goes to H comma H, this goes to F of H comma H, this goes to not. Okay, so don't tell me that these two are equal because they're not. They're messed up. Okay. Okay, you can do the exact same thing also with a matrix. Okay, you can do the same thing in the matrix. You have adjectives across and adjectives on the side, and you have filling in with zeros and ones whether or not this adjective is described by that adjective. Okay, and what you do is you look along the diagonal. This G describes this diagonal. Okay, and the diagonal is different than every single row. That's the main point. The diagonal is different than any single row, and words that do not describe, adjectives that do not describe themselves cannot be described by H, because then you get this contradiction. Okay, so there's no column, there's no word that describes this diagonal type of function. Okay, it's beautiful. It's very nice. Supposedly Grelling was a friend, a librarian friend of Russell, and he told him about this because he, saw the same self-referential phenomenon here, and Russell supposedly told it to people, or maybe Grelling told. I'm not sure on the history, but that's a very nice thing. Okay, by the way, how do you get rid of the Grelling's paradox? Okay, and the answer is, well, there's two possible answers to this. One is you ignore it. Okay, who cares? It's language, and language doesn't have to have exact meanings on every single word. Okay, that's why we have oxymorons. We say the larger half or act naturally. Those are oxymorons. Those are words, those are phrases that contradict themselves. So fine, you're using the word heterological, which has a contradictory aspect to it. Big deal. That's one possible answer. The other possible answer is to be a stickler for words and be exact about it and say, you know what? The word heterological is not a good word. It doesn't really exist. Whatever that means about a word not existing. Okay? The word heterological is not a good word. It doesn't really exist. And you won't find it in a dictionary. Okay? But I found it in a dictionary, so whatever. Okay, so two possible answers. One, ignore the problem, or two, make sure it doesn't exist. Okay, now, this brings us to so we went through three examples of paradoxes: the Barber paradox, the Russell's paradox about sets, and this heterological paradox about adjectives. And I'd like to talk about so they're all about contradictions. And before I do that, I want to tell you what a paradox really is to a logician. What a paradox is, okay, what a paradox is you have an assumption and you derive from that a contradiction. Okay? And I'll tell you what the assumption is in a second, but once you have that assumption, you go and go and go and you get a contradiction. What's a contradiction? Well, it's equal to 1 if it's equal to 0. It's true if it's false. It's a member if it's not a member. If and only if it's not a member. Okay? So you have that contradiction. Okay, and so the way to think of this, when I think of a paradox is, it's a way of testing if an assumption is a rational thing. You make an assumption and you follow logically what it means. And if you get to a contradiction, you say, uh-oh, I got to a contradiction. It's not really right. Okay, and then you stop. Okay, or if you don't get to a contradiction, then it's a rational thing to make that assumption. Or it's not irrational to make that assumption. Okay, so that's what a paradox is. Question, where do contradictions happen? Okay, and so there's this idea that I published a small paper about, and it goes as follows. You have the physical universe. Okay, the physical universe does not have any contradictions. Let me say what that means. Okay? The physical universe doesn't have any contradictions. In other words, there is no object in the world that has a property and has the negation of that property. We don't allow that. Not we don't allow that. It doesn't exist. Okay? Aristotle called this the principle of non-contradiction or something like that. And he says something very subtle in his book. He says, how does he know? How does he know that nothing can have two contradictory properties? And he says, it's not that he knows it or doesn't know it. He says, we can't have rational discourse if you don't make that assumption. You have to assume that the physical universe does not have any contradictions. Otherwise, we can't communicate with each other because we're not going to be able to communicate with each other because our ideas of properties don't match up. Okay? So the physical universe is clean or clear of all contradictions. In contrast, you have the mental or linguistic universe. Okay? what's in your mind or what you have in your language, which is something you produce by your mind, that has contradictions, okay? Everything, not everything, hopefully, but there's always contradictions in your mind. You have contradictions. On the one hand, you want that extra piece of cake. On the other hand, you want to lose weight, or I want to lose weight, okay? You want to vote for somebody who you like their 16 of their policies, but you don't like their 17th policy, okay? Or you think they're crazy anyways, and you're scared to vote for them. So you have this conflict. You want to go to school to get educated, but you don't want to go to school. You want to lie in bed and have a day off, okay? Ferris Bueller's contradiction. So your mind is full of contradictions, okay? The human mind has contradictions in it. It has conflicting desires, conflicting needs, okay? And if that gets really bad, then you go see a psychiatrist to discuss it with them, okay? Psychiatrists are not just for crazy people. They're people who have conflicting ideals in their head, okay? But stop. There is a part of mind and language which does not have contradictions in it. There is a part which cannot have contradictions, and that is math and science. Okay? Math and science are things that human beings talk about, so it's part of language, and it's also created by math, by the mind. I mean, yes, there's structure in the universe, or there's no structure in the universe, but the very fact that we find the structure, okay, shows you that we're creating it. And the structure that we find now will be different than the structure that we find in 100 years. We might have better techniques. It's definitely different than what we had 150 years ago when we didn't know about certain things. So the mind and science, math and science is part of the mental, our collective minds, and our language, okay? We communicate with each other in terms of math and science, okay? And that cannot have contradictions. And it's very simple. Why? Because parts of math and science, especially the physical sciences and whatever large parts of math, is used to describe the physical universe. So you cannot have this somehow matches up with that, and you cannot have this having contradictions and that not having contradictions. Okay, so you have to make sure that you're math and science. So you can't walk into a chemistry class and say, yes, water is H2O, but you know what? I think it's H3O also. I think maybe it's H5O too. Okay, you can't do that, okay, because that's going to bring you contradictions. Okay, you can't say it's both H2O and not H2O. Okay, you can't do a math problem and come out that the conclusion is that 2 is equal to 1 or 1 is equal to 2. Okay, because that's not what we have in our physical universe, and so we don't allow things to do that. For example, we don't allow people to divide by 0. You can divide by any other number in the world, but you don't divide by 0. Why can't you divide by 0? Because if you divide by 0, you can get contradictions. Okay? If you divide by 0, you can get contradictions, and we don't allow that. So when our children are in 3rd grade and they're learning about divisions, we teach them you can't divide by 0. Okay, now let's talk about our 3 paradoxes. The barber paradox is about the physical universe. Question: you have a rule in a village, and you get this contradiction. And the answer to the barber paradox is, you ready? That village with that rule cannot exist. Because if you had that rule in that village, you'd have a contradiction. Because you'd have the barber doing this way and that way at the same time. That's a contradiction. Okay? So we have to say that that thing doesn't exist. The set paradox, the Russell's paradox, we have to say that the collection R is not a set. Because otherwise we're going to get a contradiction. So we have to say it doesn't exist because we can't deal with contradictions. So we make up this new thing called a class, and a class is larger than a set, and it contains whatever it contains. But it can't be a set, because otherwise we'd have a contradiction. Now the heterological paradox, you can just say on the one hand, you could say, hello, that's a contradiction. My mind has a lot of contradictions, and so my language has a lot of contradictions, so we'll have that contradiction. Or if you want, you can say that word doesn't exist, whatever that might mean. What does it mean for a word not to exist? Okay, so you have to keep these three things in mind of when you're talking about paradoxes and contradictions. Very nice. Let's go further. Since we're talking a little philosophy, what is gained by doing all these paradoxes categorically? Okay, and the answer is as follows. Everybody knows that these self-referential paradoxes are somehow related. Okay, Russell knew that, and so that's why he made up this barber paradox to teach us, to show us it's the same thing as Russell's paradox. Okay, but it's a little bit more. You're not talking about abstract things like sets. You're talking about people going to get their hair cut. It's less abstract. People were able to do that. Gödel, in the beginning of his paper on Gödel's incompleteness theorem, says that his result is just similar to any other, the liar paradox, Epimenides paradox, any type of self-referential paradox. He sees the same thing. Okay, but what category theory did, and we'll talk about the history of this theorem. This is done by Professor Levier, okay, in 69 or something. Okay, what he did was he actually showed, and we're going to do this, showed how you can do this all categorically. You can show one theorem about a category with products, and you can get all these results out with ease. Okay, so that's a very nice thing. It's not just a feeling that these results are the same. We actually show it's the same. Okay, so that's one positive thing. And the other positive thing, and Levier stresses this, is that with this formalism, we don't have to talk about whether a word exists or doesn't exist. We don't have to talk about whether a village with a rule exists or doesn't exist. We don't have to talk about whether or not a collection is a set or a class, or it exists or it doesn't exist, etc. We don't have to talk about that. What we can say is we can talk about a function and whether or not this function is representable with this collection, with this set. Okay, is it representable, yes or no? Okay, so that's a very nice thing. We get rid of all the metaphysical gobbledygook of what these results tell us. Okay, and we just have a purely categorical statement about what they mean, and it's much easier, and we don't have to get into that. Okay, great. So, let me erase the board, and then we're going to start with another result, two results of Mr. Cantor about different sizes of infinity. Okay, let's go on with our list. Okay, so the next thing is, as I said before, George Cantor. I don't think it has a Cantor. Okay, in the 1880s, 1890s, a little bit later. Okay, he did some work, early work in set theory, and what he found was there's different levels of infinity. Okay, so let's go a little slowly. So we have the following idea. If there are n elements in a set, then the power set of S has 2 to the n elements. Okay, and the point is, this is much bigger than this. Okay, and Cantor was working with something else. He said, well, let's not talk about finite sets, let's talk about infinite sets. Question, is there any way in the world that S can be the same size as the power set of S? Okay, and the answer he came up with, he said, was no, it cannot be. This set is smaller than this set. Even when you're dealing with infinite size, even for finite sets, it's true, obviously, but even for infinite sets, you might think of some crazy trick that you can do, and he said, no, it can't be done. Okay, and the proof is the same as we saw for the past 3 examples of the proof. It's a little bit more subtle, but it's doable. Okay, so let's do it together. Okay, so he basically showed, let's erase this because this has no relevance. He showed that take any set whatsoever, the power set of it has less elements. Let me say it another way. Okay, there does not exist an h, a function, from S to the power set of S that is onto, surjective. In other words, usually, when you have a function that's onto, so you have a set A and onto B, okay, sometimes we write onto like that, that means there are more elements here, more than or equal to elements here, okay? There are not more elements than this, okay? So what we're saying is there does not exist an h, a function that goes onto this, okay? That is onto, okay? I want to say it one better way, okay? It goes as follows, and this is closer to his proof. It says as follows: for every h from S to power set of S, okay, I want to say that this function is not an onto function. And the way to say that is as follows: there exists a set, this is a subset of S, C sub H. In other words, it depends on H. Okay, so it depends on, you give me an H, I'll give you a C sub H. And what C sub H should be thought of is, it's a, hold on, let me just finish the sentence. There existed such that, okay, C of H is a subset of S. In other words, C of H is an element of the power set of S, but C of H is not in the image of H. What that means is it's going to be in here, but there's no element here that's going to be the image of it. So it's not going to accept that. It's not going to, this function is not going to be onto, because there's going to be some element in here that nothing hits it. Okay, so it won't be in the image of H. Okay, so that's a very, very exact statement. Let's start it over again. This set is smaller than this set. What that means is there is no onto function from there to there. What that means is if you think you have such a function, then I will find you a certificate. I'm sorry, I'll find you this C. This is to be thought of as a witness or a certificate showing that H is not onto. Okay, so we will find such a set such that C of H is a member of P of S. It's here, but C of H is not in the image of H. Okay, so that's a very, very exact statement. And now we're actually going to prove it, and we're going to prove it exactly the same way as we proved every other theorem. We're going to go a little bit quicker because we want to finish this video, and so there's a lot more to do, but we're going to assume that we saw a lot of the details of the proof before, and so we're going to go through it a little bit quicker. Okay, and the idea is as follows. Take your set S. Okay, that's what you're dealing with. You're given any set S, and there's going to be a function F. Oh, I'm sorry. Let's start a little bit before that. You ready? Okay, let's be a little bit more careful. Okay, so you assume, given that there's a function S to the power set of S, okay, then there's going to be a function F sub H. It's going to depend on this function. So again, we're going to assume that there is a function like this, and we're going to show that this function is not onto. Okay, and this goes to 2, just like before. Okay, great. I have to show you how it's defined. Okay, but before I do that, let's just do what we think is going to happen. There's a delta here, there's a not here, there's a 2 here, and we're going to have G. And G also, just like F depends on H, G is also going to depend on H, which means if you give me another H, I'll give you another F of H, I'll give you another G of H. Okay, let me show you how f of h is defined. Almost very similar to what we saw before, okay? But this time, we have to take into account that. Okay, so you give me two elements of the set, s and s prime. Damn. Okay, and it's either equal to 1 or 0, because that's what 2 has. Okay, and it goes as follows. If s is a member of h of s prime, if s is not a member of h of s prime. Okay, so this is very similar to what we had before. Last time we had this adjective describes this, or this set contains this, or this villager barbers this villager, okay? But now we're doing something else. We're saying, look, this s prime describes some subset of elements, right? So you have a little s over here, s prime, and here it's going to be h of s prime. That's a subset of elements. So we call it 1 if this s is in that subset. Very good. Okay, so we have to notice the h is in the definition. Okay, so for any purported surjection, for any purported onto, there's going to be elements here and elements here, okay, and subsets here, and we're interested in is this element, an element of the subset. Great. Now let's look at what we've always been doing for the past 2 hours. Ready? So we ask, what does g of h characterize? It's a characteristic function. So g of h of little s is equal to 1. When is that true? And the answer is when, if and only if, f of little h of s comma s is equal to 0. Because that's what the not does. So if this goes to 1, this must have gone to 0, and we go with that. What does that correspond to? If and only if, okay, s is a member, what does it mean to be 0? S is not a member of h of s. That's exactly what it says. To be 0 means s is not a member of h of s. Here we're dealing with the general case, s and s prime. Here we're dealing with just s and s, because we did that diagonal. Okay, so let me show you the subset that corresponds to what this characterizes. So we call that C of H, C for certificate or witness to the fact that H is not surjective, is equal to those S such that S is not a member of H of S. Okay, great. Now we ask the following question. You ready? Can G of H, G sub H, can G sub H be represented by any element of S? Okay, and so we ask the following question. Okay, G of H, is this equal to F sub H of something, comma, I don't know, let's call it S0. Let's say it another way. Is there some S0 that we can hardwire that corresponds to this G of H? Okay? In other words, is there some subset that comes from here, it's a subset over here, and whatever's in here will give you the same answer as whether it's in here. So if it's here, if it's in that subset, then this will be yes, and if it's not in that subset, it'll be no. Okay, well, let's assume that there is such an S0, then we can ask the following question. Oh yeah, let's plug in S0 on itself. Again, here comes the self-reference. Okay, if this was true, that would be very nice, but you know what? G of H was not defined to be like this. How is G of H defined? G of H on little s0 is equal to not f of h on little s0 at s0. Conclusion, no way in the world. This g of h cannot be represented by an s0, because if we did, we'd have this contradiction, and that's not true. Okay? I'd like to write it one other way, because we're going to see it another way. I'm going to say as follows: g of h on S0 is equal to f of h of S0, comma S0, okay, which is equal to not of f of h, comma S0, comma S0. Okay. Now that's a very strange thing. F of h S0, comma S0 is equal to not f of h of F0, comma F0. Okay, what do you call a function? So basically, not x is equal to x. Okay, that makes x is a fixed point. So notice this is the same as this. That makes x a fixed point of not. Okay, I'll explain to you what a fixed point is in a second, but the point is, the input is fixed. It becomes the same, the output is the same as the input. Okay, that's just another way of looking at it. Okay, great. Main point is, no, g of h cannot be represented by f of h. There is no subset given from here that is equal to this, that represents the same elements, that has the same, there's no subset in here, h of S0, that gives you those elements in this certificate, in this subset. So this subset, which denies itself in some sense, says, no, you're not in the subset. So conclusion, there's no way there's an onto function here, because anytime you say that this is onto, I'm going to show you it's not there. Okay, but you can see this a lot clearly with the matrix formulation, so let's look at it from the matrix point of view. And the matrix point of view is on page 121, and basically what you have is, you have this f sub h, and you're going to have, again, subsets. Let's do it carefully. You're going to have elements here and subsets there. So here's elements: little s1, little s2, little s3, little s4, little s5, little s6, okay? And here you're going to have not s1 and 2, but the subsets that correspond, that h takes it to. So remember, h goes from s to power set of s. Okay, so we're going to look at h of s1, we're going to look at h of s2, we're going to look at h of s3, we're going to look at h of s4, ... Okay, and now the output, as every time we saw it before, is 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, ... 0, 0, 0, 0, ... 1, 1, 1, 1. Okay, lots of different zeros and ones. Okay, great. Now, what does C of S? What is C sub H? Okay, this is a set of all the little s's such that S is not a member of H. H of S. Okay, so in order to be in this set, I'm going to make it with a red marker. In order to be in this set, if you're not here, if S1 is not an HS, so then it's a 1. So we cross this out. If this is a 1, that means it's in there. Well, guess what? Then it's not what we want. We want those things that don't. If it's in there, we're not interested in. If it's not there, we're interested in it. And if it's not there, we're interested in it. Okay, so this is a 1 whenever they're not equal to each other. Okay, and what does the theorem say? The theorem says is that, okay, let's just highlight the diagonal. Okay, and what does the theorem say? The theorem says that this I said R because I'm thinking of Russell's paradox. This C of H, okay, is not this row, it's not this row, it's not this row, it's not this row, it's not this row, etc., etc. It's not any of the rows in here. And the reason why it's not this row, because it's different than, it's not this column because it's different than this column right over here. It's not this column because it's different right over here. It's not this column because it's different right over here. It's different than every single column. Conclusion, C of H is not equal to F of H for any SI. Okay, it's not on any one of these columns. Conclusion, don't tell me that C of H is some member over here. So C of H is some member over here, but it's not part of what's hit over here. It's not any of the images of this H's. It's not this image because of this. It's not this image because of this. It's not this image because of this. It's not any image. Conclusion, you ready? S has less elements than the power set of S. Okay, and this is true for any set whatsoever. In particular, let's just take Cantor's theorem very, very far. We have as follows. We have S, and it's less elements than the power set of S. But this theorem works for any set whatsoever, including the power set of S. And so there's less elements than the power set of S. Okay? And that's true. This theorem's true for this too. And so we have less elements than the power set of the power set of the power set of S. Okay? ... The important point is there's an infinite amount of levels of different infinities. There's not just 2 levels of infinities. There's an infinite levels of infinities. And that's extremely important. Okay? Okay, let's go to Cantor's second theorem. This is true also for the natural numbers and the power set of the natural numbers. Okay? Okay, and we call this countably infinite. Okay, and this we call uncountably infinite. Don't want to get into why it's called uncountably infinite. Actually, anything larger than countably infinite is called uncountably infinite. Okay? In particular, this is the same size as the real numbers. Okay? The real numbers. And this is also the same size as the set, the interval from 0 to 1. Okay? It's the same size as the interval from 0 to 1. Okay? And so let's summarize what we just talked about. Okay? And the idea is as follows, you ready? The natural numbers is less than the power set, we just did that. We want something. Is smaller than the interval from 0 to 1. The interval of real numbers. So let's just remember, first day of 9th grade, teacher draws this, here's 0, here's 1. You look at all real numbers between that, and the natural numbers is less than that. Okay? Want to spend a few minutes doing this, okay, because there's one new feature in this that we didn't see before, and I want to go through it. Okay, so what does it mean that it's less than? Same thing as before. If you give me, there is no onto function from here to the set 0, 1. Again, if this set is larger than this set, then there's no onto function from here to here. Onto functions usually come from larger sets onto smaller sets or the same size sets. They're not the same size. This is bigger than this. So we get that. Okay, let's do it another way. Okay, let's do it another way. It says as follows. So this is one way, this is the simple way of saying it. This is a more complicated way of saying it. Let's do it another way. For every h from the natural numbers to 0, 1, there will be a real number let's not. There will be a real number. I think the book calls it G sub h. G sub h, such that G sub h is not in the image of f sub h. Okay, so again, this is less than this. Why? Because there's no onto function from here to here. Let's restate that. Any function that you think is an onto function, there will be a g of h such that g of h is an element in here, okay, such that it's not hit here. Conclusion, this is not an onto function. This is not an onto function, and there's no way to make an onto function. This set is smaller than this set. Okay, let me show you how we do the g of h. By the way, we're using the same notation over and over and over, so we're not confused. Okay, so let's go through it. Okay, guess what? For a purported function from here to here, okay, there is a function f sub h which goes from the natural numbers to the natural numbers to, okay, now this is the different part. Not going to deal with the set 0 and 1. We're going to deal with the set, you ready? 0, 1, 2, 3, all the way till 9. Okay, and let me tell you how this function is defined. Okay, so again, what I want to do is I want to give you a real number. Okay, and how do I give you a real number? I give you a real number by telling you the digits of the number. And by the way, this is an infinite set. This is an infinite set. This is an infinite set. This is an infinite function. So let me show you how it's defined. Ready? F sub h at m comma n. Let me just make sure I did it in the book, m comma n and not n comma m. Okay, it is. And this is equal to the mth digit of h of n. Okay, so this is a new concept. This is why we're doing this one also. Okay, so let's go through this. Question, not is m in n, but how do we use m to describe n? So, right, so we're using m to describe n. Or we're, right, so this thing is the mth digit of h of n. So again, let's go through this. H is here, you have a little guy here, n, and so h of n is some number. It's some number, it's some real number between 0 and 1. And so you want to know what that is. Okay, and this is basically f sub h, comma n, is basically, this is a function which goes from the natural numbers to the set 0, 1, all the way till 9, and it tells you, plug in your digit, plug in what digit you want to know, the first digit, the second digit, the third digit. It's an infinite number, okay? This is a real number, there's an infinite number, and I'm going to tell you what these things are. Okay, great. What do we do with these f sub h? F sub h's? Well, we do what we've been doing all along, with a little bit of a change. So let's do it. You have the natural numbers cross the natural numbers to the set 0, 1, 2, 3, all the way till 9. Okay, and you have our beloved diagonal. This is f sub h. Okay, but now we have something different. What did we do with the not? We changed things around with the not. Not of 0 goes to 1. Not of 1 goes to 0. So we did that. Okay, we did that. Not 0 goes to 1, not 1 goes to 0. We changed around the inputs for the outputs. We're going to do the same thing here. There's a lot of different ways of doing it, but we're going to make another function. Okay, we're going to call this not, but alpha. Okay, and what alpha does is it changes around the inputs to the outputs. It switches around the inputs. Now, there's lots of ways of doing this. How about this? Alpha of 0 is equal to 1. Alpha of 1 is equal to 2. Alpha of 2 is equal to 3. Alpha of 4 is equal to 5. Alpha of 9 is equal to 0. That's one way of doing it. I don't care which way you do it. Okay, I can make alpha of 0 to equal to 5. Alpha of 1 is equal to 7. As long as every input has a different output, I'm okay with it. Okay, great. Now, what does g of h do? Well, first of all, it's not a characteristic function anymore. Characteristic functions go to 0 and 1. This is not going to 0 and 1. This is going to 0 through n. So what this is actually, what is a function that you tell me what the input is, you tell me what it is, and I'll tell you what digit you have. Tell me what position you're looking at, and I'll tell you what position you have. This is describing a number. Okay, g of h is a number. Okay, and I can tell you what it is. Well, if I had h, but I'll show you. We'll do it in a second. Main point is g of h is some number. Okay, it's 0.1, 0 point. Okay, and now you want to know what the first digit is? Well, look at what it is. It's going to be, I don't know, 3. And what the second digit is? 7. And what the third digit is? 5. And what the fourth digit is? 4. And what the seventh digit, or 5, 1, 2, 3, 4, fifth digit is? 9. And what the, and this is going to go on and on. Okay, and this is exactly what we said. We said as follows. G of h is a number in here, and it's going to be different than the image of every single one of these numbers. Okay. Okay, great. Great. So we have this g of h. Now, what's the question we always ask? Can it be represented? Now, till now, we talked about representing if we're talking about zeros and ones. But now we're going to just follow exactly what it says. It says, what does it mean to be represented? Question. Does there exist some n0 such that g of h, which is a function from the natural numbers to this set of digits, is equal to, ready? F sub h, give me space, n0. Okay? Let that sink in. n0 is some number. Okay? These are both functions from the natural numbers to the digits. Natural numbers to the digits, that's here. Natural, if I if I hardwire one of them, it's a function from the natural numbers to the digits. Basically, you're giving out each digit. Every input tells you what position you have. Okay, and so we're asking, does there exist an n0 such that it is? Another way of asking it is saying, does G0 equal, is the number that's described by G0 the same as the number n0? The number that H chooses for n0. So here's little n0, is there, and the answer will be no. Okay, why? Very simple. Because if there was such a number, then we can ask, what's the n0 digit of that number? Okay, well, it'll be the same as that. 1 second, we have a problem. What's the problem? That's not defined as this. How is g of h defined? Well, it's defined as alpha of f, that's the alpha, of f sub h of n0 comma n0. So don't tell me that these digits are the same, because it was done like that. And one of the reasons, one of the requirements I had for alpha is there's no input that's the same as the output. So don't tell me, here's your input, do alpha of it, and you're going to get the same input, because look, alpha of 1 is equal to 2, alpha of 2 is equal to 3. There's no, alpha doesn't take any number to itself. And so we get that. Okay? Let's go through it again. Okay? We're going to go backwards. You ready? This function that's described by g of h is nowhere on your list here. Okay? And we showed why. Okay? What does that mean? That there is no n0 here, such that h of n0 is here. There's a g of h in here, and it's not equal to any h sub n0. That's really nice. Okay? But we got to do it with the matrix, because there you really see how pretty it is. Okay? You really see how pretty it is, and it works out very, very nice. Okay, so this is f sub h. It's on page 123. Okay, I'm sorry, we start counting from zeros for reasons that are beyond me. We count 0 from 0. 0, 1, 2, 3, 4, 5, 6, 7, dot, dot, dot. Okay, these are the natural numbers. And this is going to be h of 0, h of 1, h of 2, h of 3, h of 4, dot, 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 dot. Okay? And what the entries are is digits. They're digits. And these digits tell you what these numbers are. Okay, we're doing good. Okay, so the number is going to be 0 point. I'm sorry, maybe I shouldn't have started from zeros. It doesn't matter. Okay. Okay, 0 point. Okay, what's h of 0? Well, it's 0.53249671 8 dot 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 dot. What's h of 1? Well, it's a number. It's 0.33333333. That's a real number between 0 and 1. What's h of 2? It's 0.72416537111, etc. This is 0.500000000, etc., etc. What's h of 4? 0.2981724365. Very good. Okay, and now this is what f of h does. You tell me the position, you tell me what number you want, and I'll tell you what is the digit there. Great. Now, we not invented the number g of h, but we found a number g of h, and that g of h is different than every one of these rows. Let me show you how we found it. We did it by a diagonal. Here's a 5, I changed it into a 6. Here's a 3, I changed it into a 4. Here's a 4, I changed it into a 5. Here's a 0, I changed it into a 1. Here's a 7, I changed it into an 8. Here's a 9, I changed it into a 0. Here's a 3, I changed it into a 4. Here's a 6, I changed it into a 7. Dot, dot, dot. Okay, main point. This number, okay, let's write this number very carefully. It's 0.64518047, okay, dot, 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 okay, whatever, as this matrix goes on forever, this number goes on forever. Main point, okay, main point. This number is not on this list. This number is not on this list. Why is it not on this list? Okay, and the answer is because it's different than this number on the list because it has a different 0th digit. It's different on this number on the list because it has a different first digit. It's different than this because it has a different second digit. It's different on this because it has a different third digit. It's different on this because it has a different 8th digit, 4th digit, 5th digit, 6th digit. It's different. Okay? So don't tell me that there's some way of mapping these two sets onto each other, this onto this, okay, and you can get a list of every single real number between 0 and 1. No, Cantor showed that there is a number in here that's not on this mapping. Of course, for any h whatsoever, and so you can change the h, you're going to get a different function here. You're going to get a different matrix, but then no matter what you change it in, this will be different. Okay, so conclusion, this number is a member of 0, 1, but not in the image of h, period. Okay, so that's an amazing thing. Okay, good. We now saw 5 examples of the same theorem over and over. Let's just review. You ready? Barber paradox, Russell's paradox about sets, Hetrological paradox about adjectives. Then we saw that a set is smaller than its power set by Cantor. And now we saw that the natural numbers is smaller than the set 0 to 1, which is also Cantor's. Okay, and now we're ready to actually state the theorem in a categorical language. Okay, so let's state the theorem in a categorical language. Okay, I'm not going to be exact and formal and write down every single word, but we're going to get it very, very carefully because we've seen 5 examples of this theorem already. Okay, and so the idea is as follows. Ready? Given a category A. Okay, and let's say this category A has this product. Okay, we need a product. We need a product because we need a diagonal. Okay, and there's a function f. And this function goes till y. Okay. Okay. I'm sorry. We got to back up 1 second. I'm going to get right back there. I'm just going to go to a little musical interlude and say what we want. Okay? It goes as follows. You ready? Okay. The set 2 had a function called not, which what? It changed every input for every output. The set 0 through 9 had a function called alpha, which also changed every input for an output, for a different output. Every input is a different output. Okay, let's talk about an arbitrary set. We say as follows: here's a set S, and we have a function alpha from S to S, okay, and we want to know if there's a fixed point in there. What does that mean? Question. A function from the set with an element to here picks out one element. Question. Is there a function from there to there which picks out an element such that this commutes? Let's see what it means. It means this element that it picks out, after you do alpha of it, it's still the same element. Okay, so let's write that up. That's alpha of P of star is equal to alpha of P, is equal to P of star. Okay, if this is true, then we say is alpha has a fixed point. Okay, alpha has a fixed point. Okay, great. Let's go through it. Okay, that's for sets. Now let's talk about an arbitrary category. You have an object in the category. You have another object. You have the same object in the category, and you have an endomorphism. That's a morphism that goes from it to itself. Question. And you have a terminal object. So our category has products. Well, at least it has one product, and it has a terminal object. Okay. Okay. And what that terminal object does is it picks out, to be thought of as picks out an element here. Okay, that's the way to think of it. Okay, and question is as follows. You ready? Okay, question, not question, statement. If there is such a P, given such a map, if there is such a P, such that this commutes, then we say alpha has a fixed point. Alpha has a fixed point. Okay, great. Okay, so now let's go back to our statement. Ready? Given a category X with a product, with a terminal object, and an object Y, and an alpha from Y to Y, ready? Without fixed points. It does not have fixed points. Okay? Then, okay, I'm sorry, let me call that. Then, there is a G from A to Y such that G is not representable by F. Okay, now when we talked about representable, you talked about sets, but here we're talking about an element in the category. Okay, so what does it mean to be representable? Okay, so we have to say that. Namely, again, you have this terminal object, you have a map from here to here. This is picking out some element. Okay, and so you can say, let's just do this like this. F grows from A cross A, let's write it up like this. A cross A to Y, and if you choose, so this is the identity of A cross P. Notice what happens. A goes to A, that's fine. 1 goes to this some element that you're identifying it. Main point is A cross the terminal object is really isomorphic to that question. So now you have, here you have F, which has two inputs like that. But now you've hardwired one of the inputs and you have a map from A to Y. Question, is G from A to Y representable by F? Another way of saying that is, does there exist a P? Does there exist a P from 1 to A such that this function is the same as that function? Okay, so let's put it like this. Here's a G, okay, and here's your F, and it's built up like that. Okay, so let's go through this again. Given a category X with products with a terminal object and a map without fixed points. Okay, and you have this map. Then there is a G such that G is not representable by F. And I'm going to show you what this G is. And I'm going to show you why it's not representable. Okay, but you've seen these ideas, this idea over and over and over again. And here's the way to do it. Okay, and you ready? So let's do it. A cross A goes to Y. Here you have A. This is your diagonal. Every single time you have a product, you have a diagonal. This is your alpha without fixed points. This is your G. We've seen that diagram over and over and over again. Okay, and now let's make the statement. You ready? G is not representable by F. Okay, let's write it the way we wrote it before. G does not equal to F of, I'm just going to leave this like a squiggly line because I don't want to put an element. I'm not saying that A has a set, but it's not equal to. So it's not representable. And the proof goes exactly like we said before. If you thought it was representable by some, let's say, P, so let's say we thought it was representable by some P, okay, that chooses an element, well, that would be very nice, but this would have to work for all types of things, and so we'd have this equal for all types of things, including for P, but 1 second. P, the way this is defined, is alpha of F of P comma P. Okay. Okay. Oh, but there's a problem here. What's the problem? The problem is we said that alpha doesn't have a fixed point, and lo and behold, here's a fixed point for alpha. Okay, that's a problem. That's a problem. So it cannot be that this is representable, because if it was representable, then the way G is defined is as this. If it was representable, that alpha would have a fixed point. We assumed alpha does not have a fixed point. So again, if alpha does not have a fixed point, then this is not representable. All the theorems are the same. They're saying the same thing. Just depends what your alpha is, just depends what your A is, depends what your Y is, but they're all saying the same thing over and over. Okay? Okay, so this is a theorem that's due to Levere. I think Levere calls it a Cantor theorem. Okay, and it's from 1969, and it's in a beautiful little 5-page paper, and he proves it. Okay, the proof is it's in the book. It's page 124. It's called the main theorem about self-referential paradoxes, and it's very straight. Once you've seen it 5 times, it's very straightforward. Okay, great. Okay, I want to do it again in another context, but this is not in the category of sets. So this is a little bit more complicated, and we're going to do it. So this is Turing's theorem. Okay, this is a theorem that's attributed to Turing, and basically, first of all, it's not Turing's theorem. It's actually goes back to Davis. Turing proved another theorem. Turing showed that there are certain things that cannot be computed by a computer, and that's very nice, but he didn't do what's called the halting problem. We're going to do the halting problem. The halting problem was done by Martin Davis in the 50s. It's in the Wikipedia page, you can see that. But everybody, almost everybody, attributes it to Turing, which means basically that nobody ever read Turing's original paper. Okay, but anyways, I'm not a historian and I don't want to get into it. Okay, so let me tell you what the halting problem's all about. Okay, question is as follows. We can assign numbers to programs. A program corresponds to a number corresponds to a program. If you don't believe me, take any, I don't know, C++ program, save it as a file. You're saving it as a sequence of bits, zeros and ones. That's a number. That's a natural number. So every program corresponds to a number. Okay, and now I want to restrict ourselves. I only want to talk about programs that accept one number. Okay, and so we ask the following question. Given program M, and that accepts only one number, and input N, question, does this program halt? Let's write it up very nicely. If program M on input N halts, does it stop? Or if program M on input N goes into an infinite loop. Okay? And Turing posed, Martin Davis posed and answered the following question. Question, can I write a program that does this? Okay? And the answer is, ready? No. There's no such program in the world that can do this. Okay? And I'd like to show you how he proved it. I just want to say, these people were all working together. Well, not really working together, but Gödel and Turing were in Princeton at the same time. Okay? Turing knew about Gödel's work. Okay? And they all knew about Cantor's work, and they all knew about Russell's work. So they were all building on each other. They all knew about this self-reference things. Okay, and they're going to do this. Now, they didn't prove it the way we're proving it, but not far from that. Okay, and so I'd like to go through this proof very, very carefully. Main point is, this proof does not take place in the category of sets. It takes place in a much more interesting category, which we'll describe. Let me just clean off the board. So, Turing's theorem takes place in the category not of sets, not in computable functions, but computable functions. It does go in computable functions, but where sometimes you can have a function which doesn't give an answer. Okay, so a lot of times you put in something into a function and it goes into an infinite loop. So we have to take that into account. So we might have what's called partial functions. Sometimes you get an input and you have an output. Sometimes you get an input and you don't have an output. Okay, we're going to do this. You know what? This video is already too long already, so we're going to split this section into two different videos. That way we can spend a lot of time with the stuff afterwards also. So we'll finish up a little bit later. We'll finish up the second video.